In this video, I will be going to discuss the solution of heat equation, and this will be the most general case when the ends of the bar are kept at temperatures T1 and T2, where T1 and T2 are arbitrary temperatures, right? Okay. So starting from wave equation, C square U xx is equal to ut, right? Consider subject to first u 0 comma t equal to capital T1, right? And u L comma t equal to capital T2 for t greater than 0, right? And third condition is u x comma 0 equal to fx for x lying between 0 to L, right? And you can see that the ends of the rod are kept at temperatures T1 and T2, and T1 and T2 may be 0 or may not be 0, means T1 and T2 are arbitrary temperatures, and this method works for all cases, whether the ends are kept at 0 temperature or any other temperature, non-zero temperature. So this will be the most general case, right? Okay. And this is called the initial temperature distribution, right? Within the length of the rod 0 to L. Okay. Then to start the solution, let me take the solution of this form xx into capital Xx t be the solution, right? And let me call it equation number 1. Fine. And substituting this u in my heat equation, I will be getting this gives on substitution into this equation. I will get x double dash over x equal to t dash over c square t, right? And since these two ratios are equal and they have to be equal to some constant, let that constant be k, say, and it's called separation constant, right? Okay. Then this will give rise to two differential equations, ordinary differential equations, and those are implies the first will be x double dash minus kx equal to 0. This is equation number 2, and t dash minus c square kt equal to 0, equation number 3. Fine. And you can easily solve these two equations as they are ordinary differential equations. This is of second order and this is of first order, right? And now I am going to discuss the sign of this separation constant. As you have seen that in our last videos, that the sign of k plays a significant role in this theory or in the solution of this heat equation. So first I will take the k as a positive quantity, right? If k is positive, right? And if k is positive, then I have to select it that k is equal to p square, right? Then this differential equation becomes second becomes x double dash minus p square x equal to 0, right? And third becomes, or I should write second and third, give this, and minus c square p square t equal to 0, where I have assumed that k is equal to p square, and p is obviously non-zero real number, because if p is equal to 0, then k will go to 0. They are assuming that k is a non-zero real, p is a non-zero real number, right? Okay. Then on solving these two differential equations and then on substituting in equation 1, I will be getting This gives u x t. First I will write the solution for this, and that will be c1 cos px plus c2 sin px multiplied by the solution in terms of t, and that should be c3 e to the power c square p square t is the solution for this case if I take k positive, right? And you can see that if you approach t is for time, to infinity, then this solution will go to infinity, right? Since u x comma t tends to infinity as t tends to infinity, you can see that because e to the power the c square p square t, that will be a positive, right? And e to the power plus infinity will go to infinity, right? It means that after a sufficient large time, or after infinite time, the temperature of the rod becomes infinite, and that challenges the some physics laws, that you have a rod with some temperature on it and you leave it for infinite time, right? And after infinite time the temperature should be zero, or the temperature should decrease, not increase to infinity, right? So this is against the laws of physics, right? So I have to discard this case k positive, right? Since as t tends to infinity, hence k greater than 0 is discarded, right? Now I will take second case when k is equal to 0, right? If k equal to 0, then second and third give second equation will become x double dash equal to 0, because there is a second order ODE, and that will give me a linear function xx is equal to let me write it as c1x plus c2, right? Fine. And tt will be constant c3, right? And then on substituting this x and capital T in my solution in equation 1, that will give me, therefore u x comma t equal to product of these two, that will give me c1 multiplied by c3, that will be a new constant obviously, and let me write that capital A x plus b, where I have taken c1 c3 as capital A and c2 c3 as capital B, right? So this is the solution, right? In case if I take k is equal to 0, right? And the good thing about this solution is that it doesn't challenge the laws of physics, that if you tend t to infinity, however t is not present here, then this solution will take the form of ax plus b, right? And obviously that is not infinity, because the length of the rod is finite, right? So this should be accepted. K is equal to 0 should be accepted. Moreover, this is not a zero solution. One more thing is that, so you have to accept this solution, a non-zero solution, right? Okay. Let me take third case when k less than 0, right? Case 3. If k less than 0, then my second and third equation will give, this will become x double dash plus p square x equal to 0, and the third equation will become t dash plus c square p square t equal to 0, where I have assumed k is equal to minus p square, right? Because we are taking k as a negative quantity, then k should be equal to negative of p square. P is any non-zero real number, right? Okay. Then on solving this and this, I will be getting sine cos solution from here, and this will be exponential, negative exponential solution, and on combining and them and then putting on this equation number 1, I will be getting the solution of the form. I am writing it directly. Therefore, u x comma t from here I will obtain right something like this. Here we have exponential function with some constant, and that constant multiplied, that will give me some new constant, that will be c cos px plus d sine px, and then from here e to the power minus c square p square t is solution, right? So this will be the solution, right? And that has to be accepted, because you can see that if you apply t to infinity, then your solution goes to 0, because e to the power is negative infinity goes to 0, and that's suppose the law of physics, right? The conduction or convection laws, right? Then you can see that this solution is accepted when k is equal to 0. This is also accepted when k is less than 0. So the complete solution, or you can say the general solution, will be the sum of these two solutions, right? Okay, and I am writing the sum of these solutions. Thus the solution must be the sum of these two, this and this, and that is u x comma t equal to capital Ax plus capital B plus c cos px plus d sin px, then multiplied by e to the power minus c square p square t, right? And this is the most general solution, you can see that, right? It is containing this linear function, which is a solution obviously if I choose k is equal to 0, and this is the solution for k less than 0, right? Fine. So this is the complete solution, and it is containing cos and sin term also. Then I will be going to apply these boundary conditions, first, second, and then third, right? Using condition number 1. Let me call this A, solution number A, and I will be going to use this in my numericals, right? So you remember this solution, this is the most general solution, and then using first condition, that is u0 comma t equal to capital T1. T1 is the temperature of the left end of your rod, and then on plugging this here, I will get T1 equal to B plus C e to the power, this is capital C, C e to the power minus small c t, right? And then you can compare both sides. Either you write it directly that b is equal to T1 and c is equal to 0, because this is an exponential function, and here you can write on the left hand side no exponential function is here, or you may write it as 0 times e to the power minus p square c square t, right? And then on comparing constant compared to constant, b is equal to T1 and c is equal to 0, right? Okay, this gives b equal to T1 and capital C equal to 0. Fine. Then plugging this b and c here in my solution number A, therefore the refined solution with the lesser number of constant will become Ax plus T1 plus C0 d times sine Px times e to the power minus p square c square t is the solution, right? Fine. Okay. Now let me apply the another boundary condition for the right end when the temperature is maintained at arbitrary temperature T2, using condition number 2, u L comma T equal to capital T2, and that will give me T2 equal to AL plus T1 plus D sine PL e to the power minus p square c square t. And again you can compare that constant term is equal to constant, and this you can say that this is the exponential term because t is present here. This is the constant. Sin PL becomes constant. D is a constant. Sin PL is also constant. L is a constant. P is a constant, right? And this is a function, exponential function. Then on the left hand side, you may write, or you may add 0 times sin PL e to the power minus p square c square t, and then you can compare, right? on comparison, this will give constant equal to constant, and that will give me T2 equal to AL plus T1, and from there I will find capital A, and that will be equal to capital A equal to T2 minus T1 upon L, right? And this coefficient of this exponential function should be equated to 0, and that will give either d is equal to 0 or sin PL equal to 0. And notice this step, d sin PL equal to 0. So there are two possibilities, either you choose d is equal to 0 or the sine function equal to 0. If you choose this d is equal to 0, then what will happen? You plug that d is equal to 0 in your last solution, and that will give rise to a linear solution, right? And that is not a good choice, obviously, because the solution should be robust in nature, containing as many as arbitrary constants, right? So d is equal to 0 should not be taken, right? You have to choose sin PL is equal to 0, because for in that case you will be getting p is equal to n pi over L, and then we will plug that p here, and d will be intact, right? You should have more and more number of arbitrary constants. Do not take any constant equal to 0 forcibly, right? Unless and until there is no choice, right? So I have a choice to take sin PL is equal to 0, right? This implies PL is equal to n times pi, so that will give me p is equal to n pi over capital L, and n is obviously an integer, right? Fine. So this is my p, this is my, and this p is pi over L, fine. And then I will plug this a and p here in my last solution, that will give me, therefore, ux comma t, t1 plus t2 minus t1 times x over L and d sine, and you can see that in place of p you are going to put n pi over L, means that n enters your solution, and then you have to put n here, and you should know the reason why I'm writing here n, right? E to the power minus n square pi square c square over L square t is the solution, and you should note that n is an integer, right? And one more thing, I shouldn't write here n is an integer. Fine, okay, well that, okay. If I take n is equal to 0, right, n is equal to 0, then this will produce p equal to 0, definitely. And see that if p is equal to 0, then where is that p? Where is that p? Here is that p. No, fine. Okay. If I put p is equal to 0, if I choose n is equal to 0 here, then that will produce p is equal to 0, fine, and that will produce this solution as a 0 solution, right? And you know that this part, see here, this ax plus b is the solution due to the contribution by k equal to 0. I have to write it here, and this part is the contribution for the part k less than 0, right? So be very precise that you are going to deal with this part, this exponential part. For this part, k is not equal to 0, right? Fine. And see here, if I put n equal to 0, then p will become 0, and if p will become 0, then ultimately k will become 0. Oh, this was the case, right? Fine. P is equal to 0, then k becomes 0, and this solution corresponds for k less than 0. So from here, n equal to 0 must be discarded, right? And I should eliminate that choice from here. N equal to 0 should be discarded, 1, 2, 3, so on. Fine, because this solution, exponential solution, corresponds to this part, k less than 0, right? And obviously I have to discard the negative values of n due to the presence of this arbitrary constant here, because that negative will go out here, and this negative sign gets absorbed with that arbitrary constant, so there is no need to write negative values of n, right? So n is 1, 2, 3, and so on, right? And for that I have to put summation here, n equal to 1 to infinity, right? And that is the most general solution. is solution, right? And yes, this is called the steady state solution. Steady state solution denoted by U S. Let me denote by US. And you can see that this is a function of x. T is not involved, and you should write it USX, right? Steady state solution. And this is called transient state solution, right? And you may like to denote it by U, K, or U, any suffix, right? I'm not denoting that. Fine. And still one more condition is left. This condition, ux0 is equal to fx. First, I will explain that what is that steady state solution. Steady state solution is that solution. Steady state, as the name suggests, that means the solution which does not depend on time. And in fact, this is not depending on small t, this is depending on small x. That's why we are calling it steady state solution, right? Or stable solution, right? And our solution, complete solution, is actually equal to sum of two solutions. One is the steady state solution and another transient state solution. Transient solution or transient state solution, both words are used. And what do we mean by transient solution? Transient means something unstable, which is not intact for a long time, right? So this is transient state solution. Why we are calling it transient? Because if you apply small t tends to infinity, then it will go to 0. Means with the passage of time, it will be 0, right? That's we are calling it transient, something very unstable and which doesn't lie for long, right? Okay. So now what I am left with this third condition, and if you apply this third condition, then you will be going to use that Fourier sine series, obviously, right? Using third condition, that is ux0 equal to fx, and that will give me fx equal to t1 plus t2 minus t1 over x over capital L, and putting t is equal to 0 here will give me summation n equal to 1 to infinity dn sine n pi. I think I have missed a small x here, right? Fine. Okay, n pi x over L, and this will be 1, right? And you can bring this term on the left hand side, right? And that we'll call that function capital Fx. Then we'll apply that half range Fourier sine series, and let me write it as then dn is given by since it is a half range Fourier sine series. If you take this function on the left hand side, and then you can see that, should I write that minus and minus, okay, and then I will put equal to here, right? Now it is clear. Dn should be equal to this 2 over capital L and integral 0 to L, and this whole function, let me write it as fx minus t1 minus t2 minus t1 x over capital L, and then it is multiplied with sine n pi x over L dx, right? And then you can evaluate this coefficient dn, that will be constant obviously, depending on n. Then you will plug that dn here in this solution. That will be your final solution, right? Okay, and let me write as t tends to infinity, u x comma t tends to this t1 plus t2 minus t1 x over L, that is equal to us x steady state solution after a sufficiently large time, and the solution is equal to this steady state solution. And you can see that this is just an equation of line, right, with the one end at 0 comma t1 and the other end at L comma t1. You can see from here this is the equation of straight line, right? Because left end, that is x equal to 0, has temperature T1, means 0 comma T1 is the coordinate, and the right hand has temperature T2 means L comma T2. If you find the equation of this line, you will be getting this equation, right? So you can see that after sufficiently large time, the temperature over the rod gets distributed linearly, and that linear equation is due to the end temperature of the rod, right? You can see from here. So this is the case. I should call it general case, right? Rather calling it case 3 or case 4, I should call it general case, because every case we have done before, case number 1 and case number 2 are included in this case. In first case we have done when the ends are kept at 0 temperature, and that is included in this. For T is equal to T1 equal to T2 equal to 0 here, right? Then you will get uxt is equal to this much. And if you recall that this was indeed the solution when T1 and T2 ends are kept at 0 temperature, then our solution was uxt is equal to this much. This was absent there, right? And for the second case we had when the ends are insulated, means del u over del x at this temperature at this end is 0, del u over del x at this end is 0. If you apply that boundary conditions, those two boundary conditions here, then you will eventually get that solution, and that was, I think, this was absent obviously. Summation dn, here we had cos, right, and this was same, fine. And this is obviously the general case. It is including all the cases we have done before. So this is the most general one, and I should suggest you to use this method or this equation, this solution of this form, right? Okay, now I will take examples, right? Right. Now example number 1. We have a thin rod of length capital L with its left end insulated, right? Solve. The equation is c square uxx equal to ut, and with the left end subject to, first for the left end is insulated, and for that I have to write this thing 0 to equal to 0. This is for insulation of left end, right? The derivative with respect to x should be 0. It indicates that the flow of heat, right, or the change in temperature in the neighborhood of 0, right? 0 means x equal to 0 is 0, right? And for second condition, I am taking the right end at some arbitrary temperature, not 0 temperature. Let me take it 100, right? U L comma T equal to 100 degrees Celsius, 100 Kelvin, 100 Fahrenheit, whatever. Okay, fine. And I have to take some initial x0, initial temperature distribution, right? And these conditions are for T greater than 0, and this is for 0 to L, right? And you can see that I have used different boundary conditions, right? One end at insulation, perfect insulation, and another end capped at non-zero temperature, right? Fine, because I want to use this equation, right? The most general solution, fine. Then I have to start from this one, right? I cannot use this solution because T1 is not given. T1 means left hand temperature is not given, so I should use this. This is the most general one involving 4 arbitrary constants. Then I will use the first, second, third condition, then I will reach the solution, and you should remember this solution, right? Okay, solution. Okay, the solution to the wave equation uxx equal to ut without using any of these boundary conditions was that, right, is u x comma t ax plus b plus c cos px plus d sin px and e to the power minus c square p square t. This is the most general solution, right? And then I will use this condition number 1, using first condition, that is ux0t is equal to 0, and I have to differentiate this. If you differentiate this with respect to x, then that will become 0, that will become a. Okay, fine. That will give me 0 is equal to capital A plus differential becomes sine 0, then it will become d times e to the power minus c square p square t. Fine. And then you can compare, right? Constant equal to constant, and the coefficient of exponential function is equal to coefficient of exponential function, that is obviously 0 here, and that will give me, implies a equal to d equal to 0, right? Then I will plug this a and d here in my solution. This is my solution, right? Okay. Then u x comma t equal to b plus c cos px e to the power minus c square p square t is the solution. Refined solution with a lesser number of constants. Fine. Then using that second condition, and that is u L comma t equal to 100, and that will give me 100 equal to b cos c cos p L e to the minus c square p square t. Then on again doing comparison on both sides, we will get b is equal to this much 100, and cos pl is equal to c cos pl equal to 0, implies b equal to 100 and c times cos pl is equal to 0, right? C times cos pl equal to 0. Do not take c is equal to 0, because that will give me b uxt is equal to b, constant solution, right? And that will not be a good choice, right? Because you have a choice to take cos pl is equal to 0. That will give me cos pl equal to 0, and when is cos is 0? Cos is 0 for odd multiples of pi by 2. Then you can write p equal to 2n plus 1 pi by 2, and this L will go in the denominator. Fine, right? And n belong to integer. But since I am dealing with this p is present in the transient state solution, if you look it closely, that this p, see this p is not present in this steady state solution. This p is present in transient state solution. So taking n is equal to 0 will be a nonsense. So avoid that n is equal to 0 and negative values. So you have tried n is equal to 1, 2, and 3, so on. That is straightforward, right? And then on plugging this b and p here, then u x comma t equal to 1 0 0 plus, and that will become Cn, because now n enters into my solution. Then for if n enters into my solution and n is ranging from 1 to 3 so on, I have to write Cn, right? Linear combination of solutions, 2n plus 1 pi over 2l, right? And x, and here e to the power minus c square, and then value of p square, okay, 2n plus 1 square pi square over 4 L square t is solution, right? This is a solution, and obviously I have to put summation here, n equal to 1 to infinity, right? And you can see that ux0 is equal to fx. I have not taken fx. Let me take it some easiest function. Let me take it a constant. Ux0 is equal to some temperature. Let me call it 50. Fine. Okay. It is just a matter of applying Fourier series formula now. So I am taking the simplest case, ux0 is equal to 50. Then using my last condition, third condition, this is my third condition, using condition number 3, that is u x comma 0 equal to 50, right? Okay, that will produce 50 equal to 100 plus, putting t equal to 0 here will give me summation n equal to 1 to infinity Cn cos 2n plus 1 pi x over 2L, right? And that will go to 1. Then this 100 will appear here and minus, then that will become minus 50, right? And minus 50 equal to this thing, and then I have to use that Fourier half range sine series cos series formula. Then Cn is given by I think 2 over capital L, integration range from 0 to capital L, and this minus 50 multiplied by this cos 2n plus 1 pi x over 2L dx, right? Then minus this becomes minus 100 over L, and integration of cos becomes sine, right? And over that value, and that will go in the numerator into 2L over 2n plus 1 pi, and since it became sine, then putting limits, that will give me sine pi, okay, sine 2n plus 1 pi by 2, okay, and sine 0 will be 0. This should be the solution. And since putting, this is obviously an odd multiple of pi by 2, so it may be plus or minus 1, right? Fine, then the solution will become minus 100, L will be cancelled, minus 200 in fact, minus 200 over 2n plus 1 pi, right? And for this you can write minus 1 to the power n. If I put n starts from 1, n starts from 1, if I put n equal to 1, then this will become sine 3 pi by 2, and sine 3 pi by 2 is equal to negative of 1, fine. If I put n equal to 2, then we 5 pi by 2, and that is plus 1, fine. I think this is fine, okay. Then plugging this C in here, and that will be my complete solution. Therefore, ux comma t equal to 100 plus, I think that it will become minus summation n equal to 1 to infinity, and that will give me 200 over 2n plus 1 pi minus 1 to the power n, and where is that? Cos, the angle is 2n plus 1 pi x over 2L, and multiplied by e to the power minus c square 2n plus 1 square pi square over 4L square t is solution, fine. So this is the complete solution of this heat equation with some different boundary conditions, right? Now I will take another example, okay, and you remember this solution. We will start from here, right? Okay, example number 2, right? And for this example, you consider a rod of length, take length L, and you left end is at 20 degrees Celsius, right? And right hand is at L comma T, suppose 40 degrees Celsius or 40, right? Left hand 20 and right hand 40 degrees Celsius, and the length of the rod is capital L. Until steady state situation prevails, right? So you are keeping the left hand at 20 degrees Celsius and right hand at 40 degrees Celsius until the steady state conditions prevail, right? Means this is a kind of pre-experiment, small experiment before experiment. It's a kind of setup, right? You are putting the left hand at 20 and right hand at 40, right? And that will produce a steady state solution, right? Because temperature will be distributed accordingly, right? Because there is a temperature difference at both the ends, so the temperature will be distributed over the length of the rod accordingly, right? And then you change the temperature, means the left end which was at 20, you raise the temperature, let it become 50, right? And the right hand was at 40, then you decrease it by 30 degrees Celsius, then it becomes 10, and now the experiment starts. Then you have to find the temperature distribution inside the rod, right? So this is a kind of pre-experiment, right? Until steady state situation prevails, and then what happens after this? The left hand temperature is raised by 30 degrees Celsius, then you becomes, for left hand it will become 50 obviously, and the right hand temperature is lowered by 30 degrees Celsius, then it will become 10 degrees Celsius, right? And okay, fine. Then find u x comma t, fine, right? So I will call it, suppose I am calling it A part and B part, right? And when you apply these boundary conditions, then there will be, what happens when you apply these boundary conditions 20 and 40, lower left and right hand, then there will be temperature distribution inside the rod, and that will be taken in the B part of the experiment, right? The output of the A part of the experiment, right, the function fx, ux0 equal to fx will be given from here, right? And that will be taken in the part B of our experiment, right? And that will be, you can see that we don't have this ux0 fx here, right? And our main target is to find ux0 equal to how much, fx, and obviously that fx will be given by the output of this, right? The output of this will be here, fine. So my first goal will be to find the ux0, or we call it fx, right, from here, okay. And as the name suggests, that steady state solution, right? What do we mean by steady state solution? As I said earlier, that steady state solution means that the temperature doesn't vary due to time, right? That is del u over del t equal to 0. This represents, mathematically this represents the steady state solution, means the temperature is not depending on time, not changing with the time, right? And if we put del u over del t equal to 0, implies that del u over del t is how much, equal to c square uxx, right? Del square u over del x square equal to 0, obviously, right? And since this is c is a constant, then del square u del x square equal to 0 will give me a linear solution. Integrating it twice, that will give me ux is equal to ax plus b, fine, right? And now you know that since the left hand was initially at 20 and the right hand was initially at 40, using A conditions in A and plugging them here, I will be getting the values of small and small b. I think b will be 20 and that will be 20, right? 20 over L. Okay, using A, ux is equal to 20 plus, using this condition here, I will get 40 minus 20, that will be 20 x over L, if I'm not right. Okay, fine, right, you can plug in there, put x equal to 0, you will get 20, put x equal to L, you will get 40. So this is the steady state solution, and that will be carried in the next part of our experiment, that will become fx, right? And that is equal to fx for part B, right? And now after the steady state solution, going to this, now the new initial conditions, you can see that u0t, the left hand temperature is raised by 30 and the right hand temperature, let me call it equation number 1, and the right hand is decreased by 10 degrees Celsius, right? By 30 degrees Celsius, that becomes 10 now. And third condition, we were missing that third condition, and that comes from here, and that becomes ux comma 0 equal to that fx, and obviously that fx is equal to 20 plus 20 x over L. This is my fx, right? And now you can focus on this problem, that the left hand is at arbitrary temperature T1 and right hand at arbitrary temperature T2, right? And then this initial condition. In this case, I should use that direct formula, means after applying those initial boundary conditions, left hand at T1 and right hand at T2. If you remember that solution, I think that was containing only sine term, right? I will write that solution directly, right? Okay. Or I should use this condition again, this one, start from here, then I have to apply all these three conditions. Okay, I will start from here. The solution, right, is starting from this solution. This is the most general solution, ux comma t equal to ax plus b plus c times cos px plus d times sin px multiplied by e to the power minus c square p square t, right? Now using my first condition, u0t is equal to 50. Okay, using first condition, u0 comma t equal to 50 here, then 50 will equal to b and c. Okay, that will give me b is equal to 50, b is equal to 50, and this becomes 1, then c is equal to 0 and c is equal to 0, right? And that will reduce my solution to equal to ax plus 50 plus c0, then d sine px e to the power minus c square p square t is solution. Now let me use this condition number 2, this one. Using second condition, that is u L comma t equal to 10, right? Then if you use this condition here, that will give me, you can see that putting L here, AL plus 50 equal to 10, and that will give me A, the value of A, that will be 10 minus 50, minus 40 over L, yeah, A is equal to minus 40 over L, if I am not wrong, right? Correct. And this coefficient will be equated to 0, but we cannot take d is equal to 0, sin px is equal to 0, we'll keep p equal to n pi over L, and p equal to n pi over capital L, and obviously n will start from 1, 2 and 3, and you should know the reason why we are discarding n is equal to 0 and negative values of n, right? Because this is the part of transient solution, and it is for k equal to 1, 2, 3 and so on. Fine. Then plugging this a and p here in my last solution, u x comma t equal to minus 50 minus 40 x over L plus is that p, okay, d n sine n pi x over L and e to the power minus c square p square t, sorry, the value of p should be n square pi square over L square t is solution. And for this range, summation n equal to 1 to infinity. Fine. Now I have this solution, and still one condition is remaining, the last condition, which is for Fourier series. Then I will be imposing that condition here, and you can see that this is a steady state solution, this is a transient state solution, and that will go to 0 when t approaches infinity, right? Okay. Then using a third condition, using third condition, that is u x comma 0 equal to 20 plus 20 x over L. Fine. Here gives 20 plus 20 x over L equal to 50 minus this, and that will come here, and that will become 20 minus 50, that will become minus 30, I think, minus 30, and then 20x by L plus 40x by L, that will be 60x by L, 60x over L. Fine. And the right hand side will become summation n equal to 1 to infinity, and dn sine n pi x over L. Okay, then dn will be given by the Fourier coefficient formula, that is 2 over L integration 0 to L this function 60 x over L minus 30 multiplied by sine n pi x over L dx, and then you can integrate this, right? 2 over L first function, second function integrated cos n pi x over L over n pi over L, and then minus differentiation of this thing, that will be 60 over L, and integration of this will be cos sine n pi x over L over n square pi square over L square, and limits are 0 to L. Then plugging these limits, okay, 2 over L, and that will give me 60 minus 30, that will become 30, and that will become 30 L over n pi, and plugging that L here, that will give me cos n pi, and then cos n pi is minus 1 to the power n, and minus is still there, so that will become minus 1 to the power n plus 1, I think. Yeah, okay, and then plugging that L here, that will give me 0, right? So sine n pi is 0, and plugging this 0 here, that will give me, this is for upper limit, and then for lower limit minus 0 here, then that will give me minus 30, and the cos 0 becomes 1, that will become plus 30, and 30 L over n pi. Fine. And similarly putting 0 here, that will go to 0. Okay, fine. Then I think something 30 L over n pi will be common, and 30 into 2 60 over n pi, and we are left with minus 1 to the power n plus 1 minus 1. Fine. This is the value of Fourier coefficient dn, and you can plug this dn here, this solution. Therefore, u x comma t equal to 50 minus 40 x over capital L plus summation n equal to 1 to infinity, the value of dn 60 over n pi minus 1 to the power n plus 1 minus 1, and sine n pi x over L e to the power minus c square n square pi square L square t is the required solution. Okay, so we have discussed two examples, and that were using the different boundary conditions, right? And again I am repeating that this method works for all cases, means case 1 and case 2 we have done so far in our previous videos that are inclusive in this, right? And you are advised to remember this, right? Rather than those, you can go for this single method, and that will work for all cases, right? And this is it for heat equation in one dimension. Thanks.